Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see experimental determination of critical load for a flat plate. So earlier, right, so our lecture topic is experimental determination of critical load for a flat plate. In previous video, we had seen the theoretical calculation how that an X CR we found in that it depends on the value of M and N. Right, so that was the theoretical value by putting the M equals to 1, 2, 3, so on. First, we have taken that N equals to 1 and then we found the equation, and in that we substituted N equals to 1, 2, 3, so on, and based on that we got one envelope to find the critical load. So that was the theoretical method. Now in this video, what we will see, how to find by the experiment. So by experimental determination. So here we will not do any experimental, but I will just tell you what is the procedure to find the experiment the critical load. So first, the Southwell plot demonstrated that earlier we have also seen that Southwell plots how that is there. So the Southwell plot demonstrated that the critical load for a column can be determined experimentally without actually causing the column to buckle. So now this experimentally without actually causing the column to buckle. So column should not get buckle. Then also we can find from the Southwell plot how much the critical load is there. The critical load for a real rectangular thin plate is discovered in a similar way. Like that only, this is found for a rectangular thin plate. Okay. It was discovered the displacement of an initially curved plate from the zero load position. So means what? First apply the zero load, then start increasing the load, just like we are doing in the experiment, and see what will be the critical load when it started the what? Initially it becomes the curve. So just before the curve, means once it will start, after slightly we will allow the load or apply the load, it will get buckled. So just before that one is called the critical loading. Just here, that we have already seen in the previous video also that, but there we assume that as this as AMN. So that is the just constant. So it's not about body. That, and later also you can see in the previous video we have just removed that we differentiated with respect to AMN, right? So now what we are taking, that as just BMN. So just here it was discovers the displacement of an initially curved plate from the zero load position. W1 equals to sigma m equals to 1 to infinity and sigma n equals to 1 to infinity BMN sine m pi x by A into sine n pi y by b. So this equation is same, just here BMN is there. Now what is BMN? That depends on what? From there we found that load in terms of critical load. So what is BMN? From the previous video you can see how we will get that one. So that is equals to AMN into nx by pi square d by a square into m plus n square a square by mb square minus nx. So this is the BM. Just you substitute here for this one. So this whole into this term will be equals to the W1. Okay. The coefficient BMN increases as the compressive load intensity NX increases. Now just see here. In this case, this is here, NX is there and NX is here. So if NX will increase, this value will increase first. And NX will increase means this value is increasing. So this value becomes smaller. So if denominator is smaller, means this will increase. Numerator is increasing, means this will increase. So by both the way you can see, if NX is increasing, this BMN will also increase. So as a result, as NX approaches the critical value NXCR, now at NX what happened? NX approaches to the critical value NXCR, that already in previous video also we had seen. The term in the series corresponding to the plate's buckled shape becomes the most significant. So once that will starts buckling, but once it becomes the critical load, then that buckling will become significant. Means after that we can see how that plate is getting buckled. So before the critical load, it will not get buckled. After the once it will reach the critical load and just next to the critical load we will apply the load, then it will start buckling. Okay, so that we can signify. Give a minimum value of critical load for a square plate n equals to 1 and m equals to 1. So for the minimum load we have find, just taking n equals to 1 and m equals to 1 in the this one, right? So just substitute that value as M1 and N1 here, right? After that, what we will get here? This is W1 equals to A11 NX by NCR. So AMN is there. So AMN becomes A11 because we are taking that as M11. So A11 NX by pi square d by A square 1 plus N square, sorry, A 1 into A square. So A square by B square. So this will be what? So just here, this is just pi square B by A square into M equals to 1. So 1 plus N1. So A square by B square minus NX, right? This will be denominator and numerator is A11 NX, right? So that's it, this one. So this now, this W1 will be equals to what? A11 NX by NXCR minus NX, sorry. This is the what? NX CR and this is minus NX. So NX CR minus NX, that is here W1 equals to. Now what we can do, just cross multiply this one. So W1 into NXCR minus NX equals to A11 NX. Okay, now I'm just multiplying. So W1 NXCR minus W1 NX equals to A11 NX. Right, take this to this side. This side, this to this side. So now what we will get? W1 NXCR minus A11 NX equals to W1 NX. Right. Now divide both the side by NX. So after that, what we will get? W1 NXCR by NX minus A11 NX by NX equals to W1. So NX NX cancel. So from here what we will get? W1 NXCR by NX minus A11, which is equals to W1. So now just say this one. W1 equals to NXCR W1 by NX minus A11. So this is the simplified form of this one. Okay. So now here what we have, this one. Thus a graph of W1 plotted against W1 by NX. This one. This is the variable. This is constant. This is. So now just see, compare this equation. Okay. By this one. So like y equals to mx plus c, where m is what? Slope. X is variable with what? By changing the value of x, this will change. And c is the y-intercept, right? So now here just see the same way you can see. Here nxcr is your m, that slope. W1 by nx is variable because with respect to that only we are plotting the graph. And this is the intercept of W1. Means what? Once we will put the value of W1 by NX, this one, we will get the value of Y1 or W1, right? Then we will plot the graph, that will become a straight line. And that is only the, what? That, this one. Okay, so now let's see. Thus a graph of W1 plotted against W1 by NX will have a slope in the region of the critical load. Here just see, that is critical load is there, that NCR, right, are equals to NCR, NXCR. So this is the slope and this is the intercept along W1. Okay, so this, after plotting this curve, that only known as what? The slope, that will, this one, Southwell plot. So from here only we'll get that Southwell plot. So now see here, the Southwell plot is a graphical method of determining experimentally a structure's critical load. Means first draw that Southwell plot based on the experiment, whatever the data we are getting, right? For that, then we can find the critical load. How? That find the slope of that curve, that will be the critical load. without needing to subject the structure to non-critical loads. Means non-critical load is not required, just near to the critical load. Thus what? Find the graphically, right? How? Determining the experimental structure means once we have this curve, okay, based on the experimental data, just plot the curve. So just here, this is the experimental data. According to experimental data, plot the curve and find the slope of that curve. So whatever this curve is there, find the slope of that curve. That will give you the critical loading. That is NCRX. Okay. So the technique can be used for non-destructive testing. This just non-destructive testing is there, where we cannot destruct. Apply these things. Find the experimental data, means experimental points where those things are there. Now plot with that curve. Okay, and just find the slope of that one. You can say what is the critical load of that one, means after which that starts buckling. Let's VMP denotes a measured lateral deflection at load level P. So P stands for load here. So now we are taking that P as load, and VM is the lateral deflection. Let PCR. So now again we are assuming here PCR. There we are assumed that NX. Right, so do NXCR, don't get confused with NXCR. It's just simply that a PCR is here the buckling load. There NCR was a critical load. So the PCR is what? The buckling load. A finite lateral deflection VM. Right, this VM, P denotes a measured lateral deflection. So similarly, a finite lateral deflection VM exists because of the structural imperfection or eccentric loading. So either in a structure some imperfection is there, some defect is there, or the load is not acting at the axis of that structure, it's acting at some distance, or you can say that at eccentric loading. This is the structure. Instead of acting here, load is not acting here, load is acting here. So this is called the eccentric loading, and because of that it will get buckled. Southwell plot observed that the following approximation holds as P approaches to PR. Once P, what? The load becomes to the critical load, then what happens? So just see VM equals to A by PCR by P minus 1. So right, then VM is equals to A by PCR by P minus 1. Right, then VM will approach, in which A is constant. So just see here, if PCR by P should be greater than 1, then only this value will be. If PCR by P will be less than 1, then what happens? This will be negative. Means definitely P is the what? And deflection is there. So critical load should be more. Based on that only this value will be more, and hence we will get some lateral deflection. This equation for VM may be expressed in the form of VM equals to PCR into VM by P minus A. So again further we can just simplify and we can write in terms of this one, PCR into VM by P minus A. Thus again this simplified. If VM by P, this term, and VM are plotted again, so VM and this one. So now just see again here the same way. Okay, VM and VM by P. So means what? PCR is the slope and A is the intercept. So in previous video also you had seen this here in this equation. What is here? This one. This A11 is the slope, right? That intercept. So that's why you can see in this figure that I started from here, not I started from the origin. Okay. The same way here also you can see it's a VMA. So it's the intercept of VM, that is of minus A. So that's why it is started from here. VM, and this is VM by P versus. So after getting those points, just plot those points, and after plotting find the slope. That will give you the critical loading, or that PCR critical. Okay, so if VM by P and VM are plotted along X and Y axis respectively, the equation for VM becomes the equation of a straight line, that is equals to y equals to mx minus a, in which the slope m equals to PCR. So just draw the graph between what? Vm by p versus Vm. You will get a straight line and find the slope of that one, that m will give you, that is equals to the PCR. From measurements at several axes, axial load, P should be less than PCR. That's why we are just in here also. Yeah. Or in this also. Here, if PCR should be greater than P, that already we discussed, PCR should be greater than P, then only this will be positive and some here deflection will be there. Okay. P should be less than PCR. One obtains Vm and Vm by P as data point. Right. These are plotted along the vertical and horizontal axis respectively as illustrated in the image. So now you see, this is the Southwell plot, Vm versus Vm by P. After getting those values experimentally, just plot that points, draw the line, that line will be the straight line. After that, find the slope of that line, that will give you the critical load. That in previous we assumed that as NXCR. Here in that we assume as PCR. So that critical load we can find. Anyhow, in both the cases, that slope will be the only the critical load. This is a Southwell plot. A straight line is fitted to these points. Yeah, so all the whatever the experimental points, experimental data you will get after plotting, you will get a straight line. Its slope estimates PCR. Find the slopes, whatever slope of that straight line is there, that will give you the crippling load or P critical. Means what? Here, no need to go with the theoretical way. Perform your experiment, get the data, plot that data into the curve, and after that you will get a straight line. Now find the slope of that straight line, you will get the critical load. So instead of calculation, by verify that by experiment also, we can find the critical loading, means at what it starts buckling. Okay, the value of the constant A is of no importance. So whatever the value of A is there, what amount it will be there here, right? What intercept will be there, that doesn't matter. Why? Because just see here. From here, whatever the data will be there, it will start buckling. So from here, either this will be negative or positive or anything. That slope will be same. X intercept, either it will be from here, here or anywhere. That slope will be just here. From here also I am drawing. These lines are parallel. From here also drawing. So these are parallel to this one and parallel having the same slope. So means that intercept does not affect how much intercept is there. Anyhow, those will have the same slope and hence the same critical loading. Okay. This technique has the advantages of being non-destructive because P need not exceed the critical load PCR. So that's why it's a non-destructive, because why? P cannot exceed the PCR. Means before the PCR only the P should be, or below the PCR only the P should be there. Hence that cannot be destructive, and that's why their name is non-destructive. That's why. For this reason, it is often used in aerospace structure, fabricated or expensive materials such as composites. So in aerospace, what happens? That is too costly. If we will apply the load and it will get broken, then what happens? That totally becomes waste, that money. So what we are doing? We are just using this one, PCR. Below the PCR, we are using the P. So means that a structure is safe, or either it's a composite or aerospace structure material is there, that remains safe. And by applying that one, we can identify at what load it will get buckled. So means that is the crippling load, and below that we can use. So without breaking that also, we can estimate by using the Southwell plot, or you can say the experimentally. So experimental data plotting is the Southwell plot. Means Southwell plot is only after experimental, whatever the data we are getting, or by experimental analysis, Southwell plot we can determine, and from that we can find the critical load. Okay, so this is your reference, that is T.S. G. Maxon aircraft structure, that is Butterworth Heinemann limited 5th edition. Now a new edition also came, so that you can refer. That is not just here that I am mentioning here, that is 2012, right? So whatever the T.S.G. Maxon is there, that you can refer. In that only some contents they added that one. So it's not necessary that you just follow this only. You can go for the current edition also. Okay, so if you have any doubt, just comment on the video. Okay, I will clarify your doubt. Just come to me. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.